let's examine bonds between metallic elements or metallic bonds. So we're probably familiar with covalent bonds, which is the sharing of electrons, and we're also familiar with ionic bonds, which is where an electron is transferred to another element. But metallic bonds are a little different, and they have their own particular properties. Properties that we're familiar and are quite useful in metals. Things like that they're malleable, so that we can bend them or distort them or hammer them into a different shape. And also that they conduct electricity or allow electrons to move in their structure or through them. Well, how does each of those things happen, and why is it that we can hammer a metal into a different shape? And why is it that metals conduct electricity when nonmetals usually don't? There are some that you can make conduct electricity, but for the most part, we prefer to use metals because they have a much higher conductivity. And contrary to popular belief, the most conductive metal is actually silver. It's not gold. And copper is actually slightly more conductive than gold is. I think the fact that gold doesn't tarnish or react with oxygen or a lot of other materials kind of brought out this myth, and the fact that it was used in computer components when you really don't want oxidation happening at that one sensitive point, that made people think, oh, it's because it's more conductive. It really isn't. Copper is better in that sense. However, it does react with other substances a lot more easily, so they don't use it for every application. Well, that was a little bit of an aside, but let's talk about metallic bonds now. Now, in a typical substance, if you remember a molecular orbital diagram, you'll have a couple of orbitals, and they'll form a bonding orbital and an antibonding orbital. All right, just like this. And then we have electrons going in, and then we have a covalent bond. And usually the antibonding orbitals, well, if we have a stable compound, would be empty. And then these bonding orbitals would be full. And there's quite a gap in between where these are. Now, what happens when we have a metal and we have a lot of the same thing all together at once? Well, and all on different sides and in every which way. Well, what ends up happening is that there's so many of them all at the same energy level. Well, usually we don't like orbitals to be at the same energy level, exactly the same energy level, and interacting with other things. So what ends up happening is that these orbitals actually make lots and lots of energy levels. Just so many. All the way. When they combine with each other. And then there's just these sea of potential spots where electrons could go. And they all just kind of blend in together. Because one metal is got its electrons, but then the electrons are able to kind of move around, and we have the area down here will be occupied with electrons, and the area up here will be not occupied, just like our bonding orbitals and our antibonding orbitals. Except in this case, there are so many more orbitals. So many. It is uncountable number of orbitals. And they're all at just slightly a different amount of energy. Now, this allows these gaps in between one orbital and the next to be very, very tiny. In fact, if I was being a bit more accurate with this, I'd just draw this whole thing as a solid black blob, because that's effectively what it is. But we're going to exaggerate these differences a little bit here so that we can see what's going on. So now, when an electron gets added into this mixture, it'll sit right there. Say, well, there's all these orbitals on the different elements that have combined to make this metallic bond available to it. So it could be on this, like at the beginning of this wire and associated with that copper atom, but it could move over to the other side, to a different copper atom, say. And it's free to do that with very little energy required to jump from one atom to the next. That's how electricity can move through a wire, through a metal. And it's very easy to do that with even minute quantities of energy added, because all of these orbitals are so close to each other that it's always ready to conduct electricity. So down here we would call this is the valence band, because it's filled with electrons. And then above it we have the conduction band, which is where, when an electron is being conducted through the metal, would be. Now, in a metal, there's no distinct gap or space in between the valence band and the conduction band. That's what would separate something like, say, a semiconductor. Semiconductors only sometimes conduct electricity. So we have our valence band here, and then up there is the conduction band, and there's this gap in between. We call it the band gap. And it takes more energy to get an electron up here to where it's in the conduction band. So these will only sometimes conduct electricity. That's why they're called semiconductors. And metals will pretty much always conduct electricity, and that's why they have this particular characteristic of the metallic bond. The other thing that's interesting about metals is that they're malleable, and that is that you can hammer it into a different shape and it doesn't just fall apart. If you were to try this on an ionic solid or a ceramic, it will break. But with a metal, it will just distort into the new shape because you can bend it. Well, the reason why is that those atoms are able to just kind of readjust and slip from one position to the next, and then they're still bonded to the same number of metal atoms. They're just in a different shape than they were before. And all of these metallic bonds will stay intact. Well, ideally. And then you'll have it in the new shape. I say ideally because there is a possibility that you can fatigue a metal where there's little imperfections that creep in, and if you do it a lot, if you bend it a lot or keep distorting it back and forth, you can actually break the metal. But that's because of imperfections. If before you did that, you heated it up, then it would allow an easier movement, things slip past each other, then you can change the shape of the metal without having a lot of those imperfections manifest themselves. So, this is just a little bit about metallic bonds. So we have the difference between a covalent bond, we have a metallic bond, and we have a semiconductor, which is very similar to a metallic bond, except it has a band gap in between, so they don't always conduct electricity. With no gap, it's very easy for electrons to move up into the conduction band and then move freely about the conductor.